Uh, this is a working / informal seminar, and I will treat it as such. So people like Daryl or Cesare shouldn't be here. They're wasting their time. They know all of this. Slow me down. I have a lot of transparencies. I'm not going to get through them, so I don't care. And then 45, 50 minutes are over, I stop. The message that I want to get across, and it's basically not only mine, we are several of us here, practitioners of the art of geometric mechanics, and there's Daryl, there's Cesare here. Francois left yesterday, he's coming back. In June, there is Joris, and then there will be Henry, who's coming also. It's a general framework in which we work and attack various problems. Simply said, we are all geometers. We are all very applied geometers, which is sort of almost a contradiction in terms if you talk to a pure mathematician. But this is really what we are. And these methods have really given results. The other thing that I want to get across to you is that we have a colossal arsenal of weaponry that can be applied. And it's quite powerful. And it stretches all the way from very abstract algebra to geometry to representation theory to areas that I know very little about, like algebraic geometry. I mean, you name it. And when you look at various applications, you actually can do something about them. So since this is a seminar that is joint liquid crystals and complex fluids, I'm going to begin with this. Then I'm going to stop, and I'm going to sort of give a general blurb, probably on the blackboard a little bit. And then I show you more. So I want to show you some equations that you know about, and whose geometric structure I will talk about. And these are just examples. There are many, many, many more. I mean, to give you an idea, I mean, just about myself, I mean, there is a paper of Francois and myself that is 100 pages long. In advances in applied mathematics, 25 pages is theory, the rest is examples. They're all fluids. One example after the other. Same machine works over and over and over again. So, in liquid crystals, I would like to learn from you what the phenomenology is, because I don't understand it, and I must confess that a lot of the literature that I read, I do not understand. There is director theory due to Osin, Frank, Zucker, and Ericsson. There's the micropolar and microstage theory, which is due to Erringen, which I was surprised that people here don't know about. Eringen's books are truly a masterpiece. I'm very, very, very impressed how far he actually got, doing extremely difficult mathematics, in fact, without knowing it. And then there is a so-called ordered micropolar approach. I'm not going to talk about this because it's a combination of the two. It's very easy once you understand the other two, of L'Huillier. And they combine those, and you have equations, and we can all understand them. So I will concentrate, as everybody else here, mostly on nematic, because that's where we know more. So in the energy, this K1 is, so the kappa 1, depending whom you read, in the free energy is going to be 0. And my general setup is that I work in some domain with good boundary, smooth boundary, or no boundary, all integration by parts F0, boundary terms, etc. I will tell you something about analysis probably also. Even analysis is helped by this. So let me start with Ericsson-Leslie. Okay? So the way we handle such problems is that, I mean, there is a method to the madness, right? You look at the problem and you cut it in half. You look at the first part, which is conservative, and you look at the other part, which is dissipative. Example, you look at Navier-Stokes. Take the dissipative part, you see Euler. Then you throw this out, and you see the Stokes equation, right? And you study them separately. Of course, if this would be an audience of analysts, I would be crucified instantly by saying this, because Navier-Stokes is much easier analytically than Euler. But from the point of view of understanding, it's great, because if you understand one system and you understand the other system, you are done. Trotter product formulas, which can be implemented numerically, give you the result of the combined system. But of course, as I said, this is not realistic, because most people know that Navier-Stokes analytically is much, much easier than Euler. So this method is theoretical. Okay, so this is exactly what I did. I threw away all the dissipative terms. And we have various geometric approaches to dissipation also. We haven't gotten there. So I will talk only about the conservative part in all these talks. So here is Erickson-Leslie. And you start recognizing things, right? I mean, this piece is sort of like Euler equations, and there is a coupling term. F is the free energy. Traditionally, rho minus 1 is 1 over rho. There is nothing special about this. It's just conveniently written this way because that's how it appears in practice. I try to copy the equations the way you see them. Then you see this second order equation, but this ddt is the material derivative, alias covariant derivative for a geometer. So these are very general, this is a very general object. This is mass conservation. Here is the molecular field. The variables are the Eulerian velocity, the mass density, the director, and this is n is equivalent to minus n, which means that we really don't work on the sphere, but on the projective plane. And this has been done in a paper by François Guébalma and Cesare Tronci, and it's very interesting. I may say something about this if I ever get there. And the question is, what do you do with this? I mean, how do you understand it? So here is the energy, the way you know it, with the splay, the twist, and the bend. And the question that I would like to address, what is the variation or Hamiltonian structure of these equations? Right? And when I write Poisson brackets, I don't accept any answer like I check the Jacobi identity. This is nonsense. Because try to do it. Okay? For anything that is not totally trivial, and you'll fall in your face. So somebody who tells me I discovered this Poisson bracket and I check the Jacobi identity, as far as I'm concerned, this is no proof. I want to see the computation from A to Z. As a matter of fact, I will never do such a computation. This comes from general theory. These brackets are incredibly complicated. Okay. That's one approach. So these are, I mean, in my very simplistic way, and you know, this is part of what I want to do here, to learn from you what intuition you have about this. For me, this is a fluid in which sort of each particle carries a little arrow with it and just walks with it. Right? That's how I see Erickson-Leslie. Ehringen is completely different, and it's clearly superior. So the first key assumption is that he replaces the point particles by small deformable bodies, and he calls these microfluids. So here are examples: liquid crystal, blood, polymer melts, bubbly fluids, suspensions, whatever, biological fluids, anything works. So there are no more particles. There are sort of little pieces of jello that move around and do their own thing, and they move also, right? So there are two motions. There is a macro motion and a micro motion. So let's discuss this a little bit. So material particle P in a microfluid is characterized by its position, and I'm using standard continuum mechanical notation. Capital X, these are material variables, and the vector capital Xi attached to P. And that denotes, for example, orientation or intrinsic deformation. It could be a tensor. It could be all sorts of things, a matrix. I mean, I just try to make things as simple as possible. Both X and Xi have their own motions. So here is what the fluid does. Little letters are spatial variables, Eulerian variables, and they're given by a map that is invertible and smooth. We call those such objects diffeomorphisms that attach to every initial condition, if you wish, that is the material point, and time, another point in space, right? So this other object also does the same thing, except that now he depends on more variables. Of course, it's going to depend on X and T, but it depends also on its initial condition. Now, this is called the macro motion, this is called the micro motion. This is the hydrodynamics, this is the motion of the order parameters, whatever they may be. Okay. So, the second assumption in Ehringen's theory is the following. The material bodies, these little bubbles that do their own thing, are very small. And because they're very small, I'm going to linearize this equation. I'm going to just declare it. It has to be linear. That means that linearity, of course, is not going to be in x or t. It's going to be in psi. So this motion is going to be something, chi of x and t, some function of x and t, applied to psi. Now, where is this chi of x and t sitting? A priori, it's going to be a linear map that is orientation preserving. Why orientation preserving? Because, well, we can argue about this also, because you don't want to break the fluid. Of course, at this point you can say, what do you do about cavitation? I don't know, okay? If I have that, then I'm sunk. So let's assume I don't have this. So chi xt, so these are 3 by 3 real matrices whose determinant is positive. That's what orientation preserving means. Okay. So now, what Ehringen does, this is his jargon, depending on what group or subgroup you use of this biggest possible group that you can think of, he has names for this. If it sits in here, it's called micromorphic. If it sits in some other group, I'll tell you in a second, let's call it K3, it's called microstretch. And if it's SO3, it's called micropolar. Yeah?
I got a bit confused. Is that the gradient of chi? Or the thing that is in there, is it the gradient of chi? Or?
I haven't taken any derivative yet. Which one?
The equality there, little psi equals chi, big psi.
Yeah, it's a function of x and t. It's a matrix that hits a vector.
Okay.
It's just linear algebra. I haven't taken any derivatives yet. Right? A times x, ax, right? So this one is called microstretch. So you see, if this lambda would be 1, this would be SO3, right? Rotation matrices. But it's not. He also allows conformal things to happen. I will basically talk only about the micropolar, but you can do anything. In fact, Ehringen's theory is so general that you can put any group you want. I mean, go to your colleague who does string theory and pick up any weirdo group that they have. I can do this. It is no effort. It's the same thing. So, we are going to study micropolar fluids, and I'm going to call this group O from order parameter. In this particular case, it's going to be SO3. So now you go to Ehringen and you want to see the equations of motion. In one of the discussion sections, I made a joke that for us, because for us mathematicians, we want to get the information from physicists, from engineers, from experimentalists, what are the equations of motion so that we can start studying them. We're not questioning them, right? We're trying to understand them. This is a daunting task, and I never understood why is this so difficult, right? The simple question, give me please the equations of motion, is not an easy question to answer. And this is an example in Ehringen. So you open Ehringen's, he has 2 volumes, you open Ehringen's book, and then you see equations like this. Rho d dt, this is again the material derivative, right? Or the covariant derivative. And you're very happy if you see this because there is some kind of macro motion of the fluid. You see some derivative here, this must be a pressure, and something that couples. Okay? I'm going to come to this. So now you say, aha, so I have other variables, gamma. Now you're looking desperately for an equation of gamma. You won't find it. It's never written down in the entire book. Okay, but you find something else that he keeps telling you it's extremely important. He says rho sigma L is equal to this. All the indices sum regardless of their position, which is absolutely anathema for any mathematician. Indices in Einstein conventions have to stay in certain positions, and their positions mean something. But here they're all mixed up. So I wrote them deliberately the way he wrote them. Okay, so, well, he tells you it's very important, and you keep looking and looking and looking and looking, and 50 pages later, you discover, in fact, yes, there is a DDT in it, and here it is. Sigma k, in fact, is defined as some tensor JKL covariant derivative of yet another variable. Okay? So you have this. So in other words, this is ddt of this. Now you can plug it in here and you have an equation, you have a dynamic equation. Okay, I'm just trying to count equation at this time, at this point. Oh, I'm very happy if I see this. This is conservation of mass. This is a great equation. This is, the moment we saw this, we immediately reacted. Let me ask you if any one of you has seen the equations of the rigid body in space coordinates, not body. You know what I mean? It's the classical example. Example number 2. Example number 1 are particles. Example number 2, right? Goldstein, right? We always write the Euler equations down that are in body or convective coordinates. We write pi dot equal to pi cross omega. That means that I am the observer who sits on the body, and I describe the motion of the body as the body moves from my perspective being tied to the body, right? Where pi here is, and this is undergraduate physics, right? Pi I is equal to I omega I, where I are the moments of inertia in a principal body axis frame. So the tensor of inertia, which is symmetric, has been diagonalized. It has 3 entries, I1, I2, I3 on the diagonal. And I'm writing the equations of motion. This is angular momentum, this is angular velocity, right? And they're tied together by a constant. Okay, I'll come back to this problem. It's not as simple as it looks. Okay, but this is not what we see. When we are playing as kids, we look at it, we don't sit on the top, right? Have you ever seen those equations?
So why? We are writing equation normally in the laboratory frame, which is I sit and I watch at you.
Yes, but these are not those equations.
It's not this equation.
That's correct.
This equation, and I wonder why you think that that Erringen model is equations are better than.
Because we proved with Cesare that Erringen includes Ericsson Leslie. This was an open problem for 15 years. We have a theorem about it. I'm not going to talk about this here because this is another kettle of fish. But if you want to, I can. I talked about this in January.
Well, there is, by the way, another problem with all these equations because they don't. Here, the order parameter is on the sphere, as you said. But really, it is on the ball. It should be defined really on the ball because there are defects where it goes to 0, and this is not present in these equations, and in this I don't really understand this, but I'm afraid that here it's not present either. And the defects.
I would like to understand this.
Defects are the most important thing in the entire thing because the motion is usually it is motion that is governed by the motion of defects. After everything else comes to more or less to such a rough equilibrium, defects remain, and defects are those who move the thing.
Yes, so I would like to understand. I mean, this is part of the things I would like to understand. What are defects from a mathematical point of view? Are they discontinuities? Are they bifurcation parameters? Are they what? I don't know what they are.
They are topological defects. They are certainly mathematical objects. They are topological defects, but physically, there is a core of the defect where nothing is applied. So it is within a ball, not on the surface.
These are dynamic equations. I mean, I'm just following, and I want to see if there is some kind of a defect, a blow-up or something. I would like to understand it as a mathematician, of course.
No, he's just saying you have to
The
relax.
defect would not be described already by this equation.
So I see. So you are saying that the model is not good enough to describe this.
Well, he's saying you have to relax the constraint that n is a unit vector.
Of course, I do that. That's no problem.
And if you allow it all the way to go to a 0, you can have defects. The elements of pi 1 of RP2. which is U2.
Yes.
So you need to incorporate those. That's all he's saying. So you need to allow zeros for your n's.
Okay. That doesn't bother me.
Okay, I'm just saying.
Yeah, that doesn't bother me. I mean, I have no problem. Dynamics tells me it's going to get to 0. It's going to get to 0. That's fine with me.
Yeah, but you have diverging gradients at that point as well.
Okay. So now I have this equation. I have this equation. So this equation is really, you plug this in, and you still don't have an equation. You don't have enough variables. Now, what are the variables here? This is the Eulerian velocity. This is the mass density. Nu is what is called the micro-rotation rate. So here we are using the standard isomorphism between 3x3 matrices and R3, given by the cross product. And JKL is the micro-inertia tensor that is a function from the domain into symmetric 3x3 matrices. Now, this equation here appears as an equation of motion if you look at the rigid body in space coordinates. Right? The equation of the rigid body in space coordinates are 12 equations.
Yeah, we just think of that equation as d little pi dt equals 0, right?
Yes,
Spatial angular momentum is equal to 0.
yes, but you want to write the equation in little pi and little j, you know.
Yeah, but this, I don't understand this. When it rotates, this micro element, it should interact with the surroundings. It should align with the surrounding elements. And where is it in this equation?
These are the variables that Erringen gave me. These are the variables that Ericsson Leslie gave me was the same, u and n. And Erringen is giving me the variables, well, rho, of course, u and gamma. So these are these are the equations.
So what in this equation allows the alignment of neighboring elements?
It's the gamma, the variable gamma. So I have to comment on this in a second. So this equation you won't find in Erringen. This is the equation that Erringen would have written had he written down what he said in words. And for initial condition that is not 0. So I'm looking at this. Now I have a complete system. And the first thing I want to understand is what does this gamma do? How does it getting transported, quote unquote, by the flow? And what you see is this. This is what Erringen is saying in words. He doesn't really write it down. I don't know what happens now. Mine is on.
Is it,
It's on. I have no problem.
Just check the connector, maybe.
do you have power?
Oh yeah, I have it on the screen. It's no problem. It's the projector. I don't know what to do. You should ask the people.
If you just take it out and put it in again.
Put it again.
Because maybe your screen went to sleep or so.
I have a real problem. Ah, here we go. Okay. So please notice that in Erringen he has this gamma appears with sometimes with 2 indices, sometimes with 3 indices. If it appears with 2 indices, he thinks of it as a vector. If it appears with 3 indices, it appears as something which is valued in SO3. And in fact, what the mathematical object is that goes with this is a 1 form, which reminds you of gauge theory. And in fact, this is what it is. Erringen is in fact doing gauge theory of a very sophisticated nature. Okay. So, my question, what is the variational structure of these equations? What is the Hamiltonian structure? And what is the relation between Ericsson, Leslie, and Erringen? I will answer the first question, at least partially, and this, I can tell you the answer, I already said it, it's a paper that Francois Gebalma, Cesare Tonci, and myself have written about a year ago, in which we show explicitly that Erringen includes Erickson Leslie, which was a big point of controversy for about 15 years, with mathematical mistakes in all the papers. The solution to this problem uses the full arsenal of geometric mechanics. It's not easy. I mean, you really, you won't just do it. People try to just do it, and they all made mistakes. Okay, so let me start with one tool. And this you may have seen in some of the talks already. I repeat it again. This is a variational principle and certain equations due to Poincaré in 1901. He wrote a paper which is about 1.5 pages long. He never quoted anybody, never gave a motivation why he did it, never followed it afterwards. So we don't actually know why he did it. He begins his paper by saying, these are remarkable equations of mechanics and I'd like to tell you about them, and that's it. So Poincaré, of course, does everything in SO3, but let me tell you, there is no difference between SO3 and any Lie algebra here, be it finite or infinite dimensional. And in fact, this is why I attribute it completely to Poincaré, because in fact everything is there. So the situation is the following. It's a situation that is very special. You have a Lagrangian system that depends on Q's and Q dots. The only thing that the Q's sit in a group. For example, SO3, if you do the rigid body, which I'm going to do it, diffeomorphism group if you do fluids. So now you can restrict the Lagrangian to the tangent space to the identity, which is the Lie algebra. So you get a function on this vector space, which is the Lie algebra. And you assume that it is right or left. If you do rigid body dynamics or elasticity, you better be left. If you do fluids, you better be right. Because those are the Hamiltonians and the Lagrangian tend to be of this type. I have many other comments about this, but let me stop here. Okay. So the following four facts are equivalent. G of t satisfies the Euler-Lagrange equation for L on G, any way you want to think of them, local, global, any way you want. The variational principle of Hamilton holds for all variations with fixed endpoints. That's no news. That's Hamilton's principle. Has nothing to do with group, has nothing to do with anything. We all learned it in undergraduate mechanics. So of course we know they're equivalent. But now comes Poincaré, and he says, because I have such a Lagrangian, and which is right invariant, and because it's sitting on a Lie group, then two more things are equivalent to this. The first one are the so-called Euler-Poincaré equations, which are of this type: d dt, delta L delta xi, plus for left, minus for right, et star xi del L del xi. What is the notation? If you're not used to this, I'll tell you, it's no problem. A Lie algebra has a bracket. Commutator bracket if you have matrix Lie algebra. Vector field bracket if you're in infinite dimensions. And this is, so this for a xi frozen is a linear map. So it's add xi of eta. So the map, take the bracket with xi, is a linear map. And its star is the map between the duals. Right? If you have an inner product, is the transpose matrix, right? Okay. And notice, please, that only half the variables are used. Right? Euler-Lagrange is Q and Q dots, right? This is only half. This is the magic of reduction. And there is also a variational principle, and let me write it down. It's delta of the integral of this little L that appears here, and this little L, we know what it is. It's just a restriction of the other one. So this is, there's nothing to do. This is equal to 0 for variations that are of a certain type. Delta xi is equal to some other curve, eta dot, plus or minus, depending on right or left, xi eta, where eta t is an arbitrary path in G that vanishes at the endpoints. Okay? Now let me see what is the difficulty in this theorem, okay? What is trivial and what is not. First of all, please notice that this function here is identical to this function. Why? Because L is invariant, for example, let's say on the left, So I can multiply here by g minus 1. I multiply here by g minus 1. But g minus 1, g is the identity. I'm not going to be stupid to write it down, right? So I get L g minus 1 g dot. But g minus 1 g dot, I gave it a name. It's called psi of t. It's a curve in the Lie algebra. So this integrand, let alone the integral of the variational principle, is the same. Okay? So there is nothing to show here, right? Let's try to prove that 3 is equivalent to 4. This is so easy that we can do it in our head. Look here. Let me take the derivative of this. What would I do? It's integral from a to b del L del xi delta xi. Take the delta xi and plug it in here, this one. So this is what? It's ddt of eta plus add xi of eta. Now what do? You integrate by parts on the eta, and the add xi you move on the other side. That means you transpose it. You get an add star, right? So what will you get if you do this? You will get something times eta. What is that something? I already told you. It's going to be ddt of del L del xi with the sign changed with an add star xi of del L del xi. So as usual in calculus of variations, this is equal to 0 for all the etas that vanish at the endpoints. Therefore, that factor is 0. So 3 is equivalent to 4 is almost identical. There is nothing. So the theorem has a content. Where is it? It's here. So let me explain this. I want to prove, so now I know that 1 is equivalent to 2 because by general nonsense, right? Undergraduate mechanics. And I just proved that 3 is equivalent to 4 by computation, right? I never explained this. I just took this and I took this as given and I showed that they're equivalent. Okay, now let's tie this to this. I'm going to prove that 2 is equivalent to 4. Well, half of it is done because the integrands are the same, as I pointed out. But now, the question is, what do you do with the variations? So let's remember what we do here. So here, we have 2 points, and we have many curves that connect these 2 points, right? And we fix the 2 points, the end points. These are all the possible variations. So the delta g's are 0. Now, what do? The delta g's are tangent vectors to the group, but I'm not doing this ever, because every time I take a derivative, I bring it back to the Lie algebra by left or right translation. Spatial or body coordinates, right? This is spatial, Eulerian representation, convective representation, right? So now, if I do this, do I get all the possible Lie algebras elements or not? That's the question, right? The answer is no. What I get is no more and no less than variations of this type. All the possible delta xi's for which there exists an eta, which is arbitrary, such that these are not all the possible variations. In other words, this variational principle is not really a variational principle the way we know and love, like this one. It is a constrained variational principle. Okay? What is the result for mathematics? One needs to prove theorems in variational calculus about such variational principles. Do you know how many theorems about such variational principles exist in the literature? 0. Not 1. There are walls of books on the variational calculus, not a single theorem about such a variational principle, and this variational principle governs all the equations I know. Euler, Navier-Stokes, MHD, superfluids, liquid crystal, you name it. All of them are governed by this. 0 theorems.
Sorry to interrupt.
Yeah.
Could you just please give us some mechanical interpretation of these constrained variations? What do they mean?
They tell you that you can. They tell you that you cannot take all the possible constraints. When you have eliminated half the variables, you must be careful what you have done with the other ones. That's the moral story. So these ones are only those that come from general delta g's, right? So I have my group here, like SO3 or the diffeomorphism group, and I have variations of curves, right? G of t epsilon. Now I take the dd epsilon of those things, right? And I call those delta g's of t's, right? Like we do in our courses, right? So now these things, the group is here, are little arrows on the group, right? If I bring it back to the identity, which is exactly what I did here with the time derivative, I will get elements in this space, which happens to be the Lie algebra, it's a tangent space that is more special than the others, right? Because it's at the identity. The question is, if I do this, do I get all the possible vectors there? The answer is no. That's the surprising result. So I'm not saying that to prove this is difficult, but it's not trivial. I will not be able to speak the proof through it. It's a proof that requires some thinking, but it's a page. It's not a 10-page proof, right?
Is it related to the fact that you want to be sure that the variation at the other end is automatically zero?
Among other things, of course, because it has to be clamped down at A and at B, right? I have no choice. This is the variational principle. So when I do this here, I may lose, among other things, that if it's clamped down at A, this can go everywhere. Right? This is no good.
Because you have control only one hand.
That's right, among other things, right? Okay, so this is interesting because geometry has led to analysis. I took the point of view that I know zero analysis. I tried to do some obvious geometric thing, and it has led me to serious analytic questions. The good thing about this is that today, in structure preserving integration theory, and there is an army of people there, and Cambridge is one of the centers for this endeavor, with Ari Iserles sitting in the next building here, like one of the great people doing such things. There is a lot of simulations that are being done using this variational principle. Discrete. So everything I'm telling you here has a discrete counterpart, which I'm not going to even address. But there is a discrete Euler-Poincaré equation and everything. And there are algorithms that you can implement. And I hope that some of my colleagues will tell you about this. I mean, some of the people that I mentioned do this here, right? And the amazing thing is that these algorithms work better than you expect, which means that there must be mathematical theorems behind them. So for example, these algorithms will automatically preserve certain conserved quantities. You don't have to check them. Of course, people always check them to make sure that their algorithm is okay. You see a straight line, but you know it by theorem that it should be so. What you don't know is that the energy is conserved. In fact, the energy is not conserved. However, in every single example, and by now we have hundreds probably, that we know of, the energy always oscillates in a small band. The oscillations are irregular, but it never goes up, it never goes down. It's always straight in a small band. No general mathematical theorem to this effect exists. For example, here is an open problem, which I think is quite difficult. Okay, another thing. If you solve, let's be concrete. If I have solved these equations, after all, I have half the variables. Have I solved the original problem? Let's be realistic. I want to solve this, right? Yes. So let me tell you how to do it. It's an algorithm. You know how to do it. It's a method. First, you restrict the Lagrangian to the tangent space to the identity. That's no big deal. Then you quote-unquote solve the Euler-Poincaré equations. Now, what do I mean by solve? Well, if they're integrable systems, like this guy, then you do. Then you solve it, right? By whatever methods. Algebraic geometry methods, for example, right? But if it's not integrable, well, then do it numerically, right? We solve them. Once we solve them, you have nothing more to do. You solve the linear equations with time-dependent coefficients, g dot equal to gxc. Now, those of you who are physicists will say this is nothing, time-ordered exponentials is everything. For us mathematicians, this is more serious. There are quadratures, etc., elliptic functions, and so on. But it doesn't matter. This is something that we know how to handle. G dot equal gt xc. Remember, psi of t is known. I solved it. It's a triangular problem, right? And now I give you the solution. I give you the formula for the solution. I want to solve the L if I give you a position and a velocity. Right? Well, I tell you what it is. The velocity, the position is there, and I give you the velocity there. So I bring it back to the identity. I call this psi0. Therefore, this velocity is g0 psi0. Okay? Now, I use the psi0 as initial condition here. I use the g0 that is the identity here. Okay? So now the solution is v of t g0 gt psi t. Finished. That's the solution. These are the solutions of the Euler-Lagrange equations. I got away with murder. I solved half the equations. That's reduction. I told you I have an arsenal of weaponry, and this is one of them. I got away solving half the equations in order to have an explicit formula for the full equations. Okay.
Maybe you can show it with some simple equation.
Yes, I will show it.
Sorry, Tudor.
Just you can maybe show this.
Rigid body. I will do it.
But you say explicitly you have equation as a Newton's equation, which is two equations, and you can resolve it.
Newton, no, careful. There are hypotheses here. It has to be that the configuration space has to be a Lie group.
Has to be.
A Lie group has to be a group. I'm not saying any equation under the sun. Careful, careful. Theorems of hypothesis. Right? Okay.
Sorry, Tudor.
Yeah.
Just a stupid question. I wonder whether there is any compactness.
No. No. However, if the Lie group is compact, these equations are simpler because you identify the dual of the Lie algebra with itself. And use the killing form. Use the bi-invariant metric. So a lot of these computations become easier. That is correct. But I never assume that this is compact. So my equations could blow up in finite time. I don't know.
So for SO3, for example, this would be much easier.
I will do SO3.
Yeah. Does it apply to conservative systems? So
Yes, it's Hamiltonian system.
only.
Only. If I do dissipation, as I said at the beginning, I always cut my problem in half. Conservative, dissipative. Then I add the dissipation and I try to understand it geometrically. For example, double bracket dissipation, Rayleigh dissipation, whatever, right? And I try to understand it geometrically. That theory is developed, but not as well as this one. True. But there are results known about this. For ferromagnetics, for example, the Landau equations for ferromagnetics, you can handle them this way because you understand the dissipative term very, very, very well geometrically. But that's different. Okay, that was Lagrangian. Now I have to tell you something about Hamiltonian. Hamiltonian means you write Hamilton's equation, q dot dhdp, p dot equals to minus dhdq. But of course, this is not what is happening here because these are three equations, so it can't be Hamilton and it can't be Lagrange because it's not second order. So what is this? Right? Let me tell you a story because it's interesting. There are 2 points of view about these equations if you look at them historically. There are people who have simply said, this is an accident. I don't touch them. I don't want to see them. The great representative of the school is Whittaker. Right? Whittaker does never write these equations down in his book. Not once. But he solves the rigid body equations. So it's not that he is ignorant. No, not at all. He solves everything. He gives you the Euler angles, he gives you the attitude, and everything. I haven't given you the attitude. I have given you only this, right? The attitude equation is A dot equal to A omega. That means that the same triangular system. I solve these equations, and then with the solution of this, I plug it in here. Linear equation with time-dependent coefficients. Exactly as I said before. It's the same phenomenon over and over again. Okay, so the other extreme is people who are obsessed by this for good reason. And the last person who was like this and who came dangerously close to solving it is Hamel. Hamel's 1949 book that has never been translated into English as far as I know. Mechanics is one of the first books in the Grundlehren, volume 3 or volume 4, something like this. Basically, studies this equation and his brothers. I'm exaggerating, but it's this. And he does everything under the sun to try to understand it geometrically. If somebody would have told him, don't think vector spaces, think Lie algebras, he would have done it. He was very close to doing it. The first time, let me give you the history of this. The first time these equations have been stated and not explained to be Hamiltonian is 1975. This is recent history, right? Most of us, not all of you, were alive. Many of you were not. You were not born yet, but that's okay. But some of us were alive at that time, right? We were already born. So this is 1975, right? And this is Sudarshan and Mukunda. And they simply say, here is a Poisson bracket, here is the kinetic energy, 1/2 pi dot omega, check, F dot equal to F cross H, F bracket H, and you get these equations. No explanation. Okay? Now today we know much, much more, and I will tell you about this. So the point is that we need more than Q's and P's in order to understand this, and this object is called the Poisson manifold. So a Poisson manifold is a phase space manifold such that the functions on it have a bracket, and the bracket is functions, of course, can be multiplied. There is a bracket relation that forms a Lie algebra, so it's bilinear, it's Q-symmetric, and satisfies Jacobi, and the two structures talk to each other. Otherwise, it wouldn't be interesting. And they talk to each other through the Leibniz identity. The bracket is a derivative. If you freeze one function, that object is a derivative, right? And that has consequences. It has consequences because since it is a derivative on functions, it must be given by a vector field. That vector field is called the Hamiltonian vector field. So even though the bracket is not invertible, the matrix is not invertible, I have a Hamiltonian vector field. I don't have dq/dp, but I have Hamilton's equations. Okay, in addition to that, there are things here that are called Casimir functions. Those are functions that are in the center of the Lie algebra. This we never see in classical mechanics. Because that means, what does it mean to be center? It means it's a function that commutes with everybody. Here is one that you know from rigid body mechanics, and this is norm of pi square. Let me give you another one that you know. It's entropy in fluid dynamics, right? And I can give you other objects like this. Okay, examples are symplectic manifolds where we have dq/dp, for example, cotangent bundles, right? And there, it's very simple. You take the derivative of the function. The two form is non-degenerate, therefore it determines a vector field. You call this the Hamiltonian vector field. This is this relation here, right? This is must be equal. Of course, it was too late last night. Xh must be equal to dh, and then the Poisson bracket is given in this way, and that's okay. But there is another example, and this is the second most important example, and this is called the Lie-Poisson bracket because it was found by Lie in Kontinuierliche Transformationsgruppen explicitly and promptly forgotten. In the 60s, it was rediscovered by about 5 people. Berezin, Arnold, Kirillov, Suryo, Constant, at least. More or less at the same time. It's only in Lie, and it's not implicit, it's explicit in the middle with a number, right? In the middle of the page with a number displayed. You cannot argue, it's not there. Okay, so what does it do? Let us take a Lie algebra and let us take its dual. That's the dual vector space. I'm taking two functions, f and g, on this Lie algebra. And I take their derivatives, right? So what is a derivative at a point? It's a linear map between the space of departure to the reals. So it's a linear map on the dual. So it's in the bidual. So if you have an infinite dimension, it's a vector, right? By linear algebra, first year, right? So that means that del f del mu is a vector. So I use physicist notation because if I'm in infinite dimensions, this is literally the del f del mu that you know and love, with the integral and everything. It's literally that. So, then you do the following thing. You take del f del mu, you take del g del mu, these are elements in the Lie algebra, you are allowed to take their brackets, and mu is a functional. So this is the pairing between the Lie algebra, the dual of the Lie algebra and the Lie algebra, right? This functional acts on this vector and it gets a number, right? So this object now is a Poisson bracket, and that is a major theorem. And the understanding why this is so is extremely important. Okay, so now you want to write Hamilton's equations down. They can be written down. They're very, very beautiful. What are they? They're Lax equations. All of them are Lax equations. Every single one of them has nothing to do with integrability. These are Lax equations. Like Epifanio said, if you are in compact, star is no more star, you change the sign because it's Q-symmetric, and what do you get? You get the bracket of mu with del h del mu. You get mu dot equal to mu, comma something. This is a Lax equation, right? All of them are like this. Okay, so you have to trust me that this is so. This can be proved by hand, but this is stupid. Of course you can prove it by hand, but why, right? There is a deep reason why this is so, which has to be understood. But in Poisson, and there are other ones. I don't want to go into this. If you fix another one, it has to do with integrable systems. The point that I'm trying to make is that in Poisson manifolds, you have a picture. Here is your manifold. And now you play control theory. You say, I want to go from here to here, if I can, by a broken line, all of whose segments are pieces of integral curves of Hamiltonian vector fields. Can I get from point P to point Q by connecting it with chunks of integral curves of Hamiltonian vector fields?
Finite number or countable?
Finite, usually. I'm talking finite dimensions. Infinite dimensions, the theory is in very bad shape.
Even in finite dimensions, you could have.
You could have.
Countable
Yeah.
number.
Yeah. In principle, you don't care. In principle, you don't care. In principle, you don't care. You can have an infinite number that gets smaller and smaller as long as you get there. But you must get there, not in the limit. You really must get there. That's the point. You must reach it. Okay. Then you say that these two live in the same symplectic leaf. And the fundamental theorem that I put there in red is the following. Every Poisson manifold stratifies. It gets cut up in this symplectic leaf. They're all connected. These symplectic leaf are the reachable set in control theory language of a given point. They are what is called Poisson submanifolds, but they are not submanifolds themselves in the strict sense of the word, of differential topology. They are only immersed manifolds, and a little bit more, but I don't want to get into this. And the tangent space to these manifolds are the space of all Hamiltonian vector fields. So unlike in symplectic manifolds, if you take a point and compute all the Hamiltonian vector fields, you don't feel the whole tangent space. You feel only a subspace. That's the space that's tangent to this manifold. Right? This is what's going on. So, this concrete example, if I give you R3, I take the Poisson bracket, which is minus pi dot grad f cross grad h. This is f with h, where I identified SO3 and this dual with R3 because they're in 3 dimensions, right? And the cross product is the Lie bracket in this case. So I have R3, it's a Poisson manifold. I can write Hamilton's equations. If I take h equal to 1/2 pi dot omega, and I plug it in here, these are the equations that I get, Euler's equations. Okay? What are the symplectic leaves? They are the concentric spheres. Please notice that there is one of them that collapses. It's 0. All these manifolds are symplectic, therefore they can be only even dimensional. They jump in dimension, but if they jump by 2. Guaranteed. Right? So, the symplectic leaves are the spheres, and the spheres, incidentally, are given exactly as the level sets of this map, which is the Casimir function. All of this is no accident. None of it is an accident. Absolutely nothing. Okay, so let's do one example. Let me do this, the free rigid body. I'm going to go by the book now. I have a vector, and I have my skew-symmetric matrices. And there is an isomorphism. The isomorphism is take the cross product. That's the isomorphism between them. My group is SO3, and I have to compute the analog of the conjugation map, and that is given by this isomorphism simply by the multiplication with the matrix. Then I have to compute the coadjoint map, and everything has a sign change, but that's all there is to it. I write the Hamiltonian in this form. If I write it in pi's, that means that I want to use Lie-Poisson theory, Hamiltonian theory. If I write it in omega, that means I want to use Euler-Poincaré theory, Lagrangian. And if I don't want to see this, if I want to see the A's and the A dots, which I could do, which I haven't written down, I could write it also in this form, and then I could plug in the attitude matrix. And what is happening here is that this formula generalizes, has vast generalization. So the rigid body that we know and love is one example in a colossally big family of integrable systems. Every single semi-simple Lie algebra, every given Dynkin diagram has a rigid body on it. And that rigid body, in fact, has many, many rigid bodies on it. All of them are integrable. So if I give you SLNC, there is a rigid body equation going with it, which is integrable. This is the results of Fomenko and his school. I give you E8. It's integrable. Right? The exceptional Lie algebra. E8. Okay. So, what I have shown you is that the free top equations, the rigid body, are geodesic equations of a left invariant metric on SO3 determined by the quadratic function given by I. It's just geodesic motion. This is the result of Arnold of 1966. And I wrote here the bracket, and I told you what the Casimir is, and here is the solution of the problem. I take spheres that are constant, this function, right? Because they are conserved by anybody. They are sort of more conserved than others, right? So they're certainly commuting with the Hamiltonian. And then I have the ellipsoids of energy. And I intersect them. And I get this picture. I put this picture here because you see it in any other book to bring home, again, the message. How do you obtain such a picture? I mean, don't draw it by hand. Do it, really do it, right? There is a book that is addressing this subject. Heyerer, Lubitsch, and Wanner. That has to do with structure preserving algorithms for ODEs. And they come over and over and over back to this example. And they show you that they keep using various fancy algorithms that will not give them this picture till they get to the ones that preserve the Hamiltonian structure and they preserve the group structure, preserve the entire geometry. Then you get this. So to get such a picture is not easy. Really, if you want to do it honestly, not drawing or intersecting just by graphics, ellipsoids with something. Do it numerically, but it can be done. So that's this. My time is over. We can keep talking. The next thing would have been to show you fluids, and the next thing would have been to show you Korteweg de Vries, so that you know how to see also wave equations that are like this. All of them go the same way. And this is just the easy theory. The theorem that I gave you about Euler-Poincaré and Lie-Poisson does not apply directly to liquid crystals. There is a vast generalization of that theorem that then applies. And even that theorem is not the most general one. And there are more and more and more examples that you can do. You can do, for example, Young-Mills fluids. if you want. I mean, I don't know a system that is good that is not in this form. And if I see equations or statements that do not preserve this geometric structure, I'm becoming immediately very, very suspicious of them. Because experience has taught me that every single time this happens, it's good. Concretely, the Lee-Poisson formulation or the Euler-Poincaré formulation of the Erickson-Leslie equation has led very recently to a proof of existence and uniqueness, which previously was not known. And this uses a reformulation of Erickson-Leslie equivalent to this that preserves the geometric structure. How does what does analysis have to do with this? It doesn't, strictly speaking. But it organizes your mind. It tells you what are the correct variables, for which variables should you look for estimates. Right? Then it's a problem of analysis. But at least it tells you, don't look there, look here. This is where you should look. And this is where if there is something, that's where you will find it. So let me stop here. I mean, there's much more. We can keep talking in these informal seminars as much as you want. I can keep going for hours and hours. It's no problem. Thank you.
Yeah. So, Tudor, would you, in answer to Lynn's question, so it seems to me it's impossible with the Hamiltonian flow to get n squared to go to 0. That's just impossible.
Yeah, it's conserved.
But what that means then, if n equals 0 or n squared equals 0 is a defect. That's what you said, Lynn, right? N squared equals 0 is a defect?
Yeah.
It's a defect has n squared equals 0 along a line in 3D or at a point in 2D. So it's a characteristic of a defect that doesn't characterize a defect.
Oh, yeah, okay, that's fine. You're absolutely right. I feel the same way.
But you need n to go to 0 at a singular point, which is the...
Yeah, but that's not what I'm coming to, though. What I'm coming to, then, is that defects must be created by dissipation. Right? Because the Hamiltonian theory cannot create defects. So what dissipation creates defects?
Well, I don't think so. Well, Hamiltonian, of course, it's not this realistic system is not Hamiltonian at all. But if you imagine this non-dissipative motion, I don't see why wouldn't it create defects.
Because, we just got that
because
saying.
any
N squared is always 1 in the Hamiltonian system.
You can prove it.
Therefore, if it's not going to be 1, then it has to have been created by dissipation.
That's if you start in the ordered phase.
Well, okay, an example. Take this on a sphere. Take a pneumatic on a sphere. It must have defect. Even in a state, even in a equilibrium state, it has a defect. So it doesn't matter really what is dynamic.
So then the defect is in the initial conditions.
No. Topologically, there must be a defect.
I know.
It is
but
like
start my initial
conditions.
conditions.
You cannot. It is.
You
cannot comb. You cannot comb a dog without creating a defect.
We're not going to comb the dog. What we're going to do is we're going to start the problem of the motion of a liquid crystal on a sphere. Okay? And you say, well, you can't start it without having a defect.
Yeah, it has to be an initial condition.
We put
You're
the
correct.
defect in.
Yeah. Yes.
We put the
Has to
defect.
be in the initial condition.
Or if you want to describe the planar case, the flat case, if you quench from the disordered phase, then you will inevitably, if you quench fast enough, you'll have non-equilibrium pieces.
Yeah, so there will be then
So you put it in the initial condition. Yes.
defects in the initial condition. But then the Hamiltonian theory can apply. Okay? So then it becomes
But it'll have
like,
to be, has to be
like-
adapted.
it becomes
to-
like point vortices then.
Yes.
Yeah, okay. So
Right.
this sounds like, an ideal problem to work on. is to take.
You have to worry about the boundary conditions at those zeros and all of that,
Yeah.
which is good. Yeah, it's a great problem.
Yeah, and defects, Hamiltonian motion of defects would be solvable. It is not.
Yeah, has this problem been approached?
No, not in any even moderately rigorous way. No.
Yeah, I think that's
Well,
a good
that's
possibility.
why we are all here, right?
Yeah, right, we're all here. Yeah.
But it is not described by these equations.
How do you know that?
Now, this is
How I know? Because these equations operate on a sphere.
Oh, yeah, but
Not
once
the- here-
once the defects are there, then they're going to interact with each other through these equations.
You don't need the curve 2D case. You can have a bulk case, but if you quench, you will inevitably form defects. It's not an equilibrium system. So you have to if you model it starting in the ordered phase, you have to put in defects in the initial conditions as you say.
Yeah, I think it's a great problem. It's really analogous to the point vortex problem for the Euler equations, and that problem is completely killed by this method. Okay, so I think moving on to kill the next problem, and with defect motion, I'm sure that this method will work beautifully.
Oh, I don't see the role of the free energy here, the elastic free energy, due to the distortion of the nematic vector field, because this, of course, is crucial in the creation of the defect. We know that.
Can you
the
speak up if you find it? I can't hear.
Well, I don't see the role of the distortion free energy, elastic free energy in this theory, and that, of course, plays a crucial role in defect formation.
Let me tell you what my take on this is. I have given you a Lagrangian, right? The Lagrangian is kinetic energy, and you put in the potential energy whatever you need.
Yeah, but one has
So it's in there.
Yes, I agree, but one has to be a little bit careful because these are singular Lagrangian. Because the density per unit volume of the distortion elastic energy blows up at a defect. One.
So now we're coming back to Daryl's point. It's not C infinity.
Yeah.
It's not C infinity.
All right.
Absolutely not. So that means that, to put them together, that means that if you were to compute this Lagrange or this energy at these points, which are singular, you're going to blow up. So that means that we have to do something. But this is happening also in point vortices,
Yeah.
right? You're not allowed to have...
Finite energy. So you can prove that at a point effect, the density blows up to the total energy stays finite, and this is the reason why actually you can even minimize the energy with defects in the domain.
I see.
This is true in 3 dimensions, it is not true in 2
It'll
dimensions.
connect now with the Arrington
To
theory.
dimension, the
and,
energy
and
goes
so I
up.
think that'll
Not only the density, but also
keep
the
talking.
energy.
No, if you ask me what kind of, for example, what we did is two-dimensional, Erickson Leslie, and indeed the spaces are far from C infinity. There are certain Sobolev class spaces. I can show them to you.
Yeah.
And there are certain, certain number of derivatives, and there are not many.
I can talk on that.
It's quite
We'll understand.
quite limited. So it's certainly not C infinity. And for example, there are these equations of Forster. There's this classical paper in the 70s. 4 authors, Forster, Swift, I don't know how many. It is reproduced in the last edition of Landau and Lifshitz. And those equations, we could prove that they blow up in finite time. It's completely in agreement with what you're saying. So the solutions of those equations blow up in finite time. My problem with those equations is I don't understand, if I take out the dissipation, I don't understand the geometry.
Okay, so Tudor, first of all, it's not entirely true what you said, but the point about it is that if we have this set of equations, geometrically interesting, self-consistent equations, and we don't yet have dissipation, then we're just at the moment when all the interesting things happen because then we damp and drive a nonlinear Hamiltonian system, and all kinds of things can happen then. So it's, you know, we're just separating out, like you said, cut the problem in half. We first use our favorite method that, you know, develops all this geometry on the Hamiltonian side, and then we damp and drive. Okay, and we don't overdamp. We want to balance damping and driving, right? So, and then all kinds of things are going to happen. And I also have another comment about this defect thing. You didn't get to the, so I keep forgetting this word, complex fluid part of the talk. I'll say something about that on Tuesday. But the point about it, the complex fluid part, is that if you don't have any motion of the medium, so it's not a complex fluid, but a complex medium, okay, like Chesery calls it, then the equations for the equations for such a medium, for the order parameters of such a medium, can be mapped over into a situation where you then see what the defects are, because they get mapped over into a gauge theory, okay, in which, so now I'm trying to speak this physics language, right? They get mapped into a gauge theory where there is a connection form, corresponds to a vector potential, and I believe, and most people I think believe, that the curl of that vector potential being non-zero has something to do with the density of defects. Okay? And the other feature about it is that the variable, which is the pi type of variable conjugate to the angular velocity of the associated with the order parameter, is a gauge charge. Okay? And it fits into the Yang-Mills it fits into the Yang-Mills part of the interactions of gauge charges and vector fields just perfectly. So maybe that can be a place where we talk about the defects and definitions of defect, and you know, I think we need to be careful about the definitions of defect, and you know, and then specify problems that can fit within the framework of those definitions. I like.
Well, Ehringen has the vector potential. It's the gamma.
Yeah, the gamma.
The gamma in Ehringen is the vector
so the
potential.
gamma is the connection form.
Yeah.
Okay, and what was the other one? Did you have a DLD nu?
Yeah.
Okay, DLD nu is the charge,
Yeah. That's right.
the gauge charge. So these things are dangerously close to interesting physics, because on top of it, you can put in topological, you know, fundamental groups and so forth, and topological properties. I think we're not off the track very far here. I think we can meet.
Another question. When you said the Ehringen theory has Ericsson-Leslie as a special case, do you mean just the conservative part or the
Conservative.
conservative?
Purely conservative. We haven't looked seriously at the geometry of the dissipation in these equations.
So it would also not be able to decide between the Harvard and the Leslie-Ericsson model. I think that differs in the
I know.
in the dissipative
The
part.
dissipative, I know.
The Harvard theory so far,
And it gets
we've
much
been
more
looking deeply into the Harvard theory and the way it could possibly fit into this framework, but so far we failed. At least I failed in this. I would be really interested
So even
in
the
talking more about the Harvard theory.
I don't know much about it, just know they are different and no one has
Yeah,
shown that they are
yeah.
the same.
No, they're not the same.
No, I think no one could show that.
I think it's not the thing. I mean, they insist in having this symmetric stress tensor, which I wonder what kind of stress tensor for the elastic stress tensor in liquid crystal theory do you get?
What's the question?
What kind of stress tensor? If you ask me about this Forster model, I can tell you. I mean, I know exactly what, because I use the same model. the one that they write. There's the
Yes.
sigma R and the sigma D. And
I can't remember what kind of stress Erringen has.
Erringen has
Something like gamma.
the gammas
With the
are
LD
in
gamma.
the,
That's right, isn't that it? It's gamma
Yeah.
contracted with the LD gamma.
yeah.
Then it's a
You
tensor.
end up with the free energy that's a function of gamma and the macro inertia tensor, and the geometry gives you the force that's acting on the fluid. Now, if you're asking for the specific explicit form
Expression, yeah.
of the tensor, then did we actually look at the explicit form of the stress tensor?
No,
Is it
but we
possible-
proved that under certain hypotheses that are the starting point of Erickson-Leslie, that energy of Erringen can be written as a function of n and nabla n. And that's a theorem. It's not obvious. So we get back the one that we know and love, the one with the case.
So yes, in a way, it is reminiscent of a connection. This gamma.
Yeah, right.
No, the gamma is literally a connection.
Yeah,
It's literally a connection.
My simple-minded mind.
Yeah. No. I mean, when I say connection, I literally mean it in the technical sense.
No,
And there are curvature terms appearing and everything.
Because it is a distortion. I think.
Yes.
but the curvature terms, and they come from taking the derivative of
The derivative.
gamma,
Yeah.
those are the ones we want to associate with densities of defects, but in a really precise way. As when, for example, you have one defect. Okay, because the curl of the exterior derivative of this gamma 1 form is an area element, and it's got some number associated with it, and you sort of think of it as the density, because it has an areal density of the defects. That's just sort of like a fairy tale. I'd really much rather just understand how do you describe one defect, and then how they interact without actually, even without the motion of the fluid, it might still be.
Yeah, of course.
Yeah.
I mean, we can always turn off the macro motion. It's no problem. It's absolutely no problem. The whole structure goes through. No problem.
Yeah.
The words that you're using are also very reminiscent of dislocation.
Oh yeah, sure, the same. Yeah, it's any.
I mean, getting some kind of
It's any
yeah.
non-zero curvature of a 1 form. Okay, that I think it's also a dislocation, right? You do it if your 1 form doesn't have zero exterior derivative.
Yeah,
Then when you do an integral around
Right.
the loop,
you get the Burgers vector or whatever.
you get Burgers vector in case of dislocations, but you don't get back the same value as you started with, because integrating around the potential field, you come back to the same value. If you're integrating a gradient, right? But if the object has a curl, right, then you're not going to get the same value.
Yeah.
And that's another thing I think there might be all kinds of singular things that are going to be appearing that you guys will have to explain, like monopoles and Burgers vectors, and objects that are just kind of suggest things that we can think
Well, the
about.
liquid crystal has monopoles. Pi 2 is also non-zero.
Yeah.
So it's actually the most interesting case.
Maybe if I may, another little remark in this. So I don't know of any rigorous, if you want, analysis of the case that was discussed here, where there is flow, but only on the order, on the nematic director, if you want, level, there is a huge an effort from analysts. So the heat
like
flow.
Fenghua, right?
Sorry.
Like Fenghua.
Well, yeah, heat flow and harmonic maps.
Yeah, right. Uh-huh.
So that would be dissipative because there's energy balanced by dissipation. But there's a huge body of work on that.
That's another really interesting connection. The harmonic maps are just a step away from the two-dimensional pneumatic equations.
Yeah.
I should say two-dimensional, either two-dimensional planar case static or in static and with one spatial dimension. Just by changing R cross R for your two variables into C, that complex plane, bang, you go straight over to harmonic maps.
Now, physicists call it XY model.
Oh, okay.
No, that's U1, but this is when we talk about height and this up.
Yeah.
What is even more interesting is if you have the defects are not excitations, but are actually properties of the ground state. Namely, they're energy minimizers. So then you have defective structure in the ground state, not because it's required for any topological reason, but because it's minimum energy. That happens in these harmonic maps, and it happens in physics as well.
That's great.
For example, the ground state of a crystal on a torus, embedded torus, bicycle tire, two torus, but embedded in R3, it has disclinations in it. Because they lower the energy. Because, for example, 5-fold coordinated things like to live on the positive Gaussian curvature outside of the torus, and 7-fold coordinated things like to live on negative Gaussian inside of a torus. So these defects are not excitations, they're intrinsic property of the ground state, because they're energy minimizers. And there are some examples in harmonic maps where the minimizer is a defect not required by topology.
Not required by topology.
Yes. But because you can lower energy with defective structures. Right.
Some
Energy functional. Certainly
some
energy
results there, by the way, become completely wrong if you allow if you go off this U1 group into the full circle.
Yeah.
Say, I remember when we go Brazis would call it that there is a situation, there is a minimizer to 2-point defects with a line connecting them. But it is not a minimizer because because this line would collapse.
Yes, it depends on the precise problem, but there is quite a number of
Well,
examples.
in this precise problem, this is point defects in pneumatics. This
Yeah.
two H.
Yes, but I can give you lots of other examples where the defects are energy, several other examples where the defects are energy minimizers.
So I have a question for you. Very close to this Leslie Erickson theory or an Erringen theory for SO3 lies the principal chiral model. Okay? Do you have to know, does the principal chiral model have hedgehog or monopole solutions? I'm just thinking of places you can transfer technology.
What is it, SU2 left? Because just SU2 left or something like that.
Yeah.
So it has an U for the model. It's going to be yes. It has an SO3 in it, which has an S2, so it has non-trivial
Yeah.
which are point defects, non-contractible two spheres.
Yeah, so very close to it. The chiral model is a baby version of the SO3 Erringen model. Right? In the baby version, in the sense that there's no potential energy, and that moment of inertia-like quantity is a multiple of the identity. That can be extended, so it's not a multiple of the identity anymore. And then it also fits with the harmonic maps. And if it also has these...
I turned it off.
Yeah.
I don't know what's going on.
Okay, so it fits also with the harmonic maps, and it has these singular solutions. So that might be a common ground we can talk.
Ladies, please. Shall we move the discussion up to coffee? What do you think?